Hey, Professor, how's it going?
Good, how you can?
Good, good. All right. So yeah, I got your email, and I made as much corrections as I could during the 40 minutes I had. So I got them printed out right here.
Oh, okay. So, so you added explanation of the Redfield.
Yeah, I only focused on the graphs that are like newly made. The ones I got from my poster, I figured I could easily add them. So I only focused on the first 6-8 figures right now.
Okay.
But I'm going to add explanations for the later half of my figures tonight.
Very good, very good. And after you're done with this, you may start composing the text that explains all of them at once.
Okay.
I'll bring. You can stay nearby screen, or you can just watch your. Just there will be a colleague who needs to set up a connection. He will use this camera. He will connect remotely. So for the panel instead of figure, yes, you already choose. Okay, yes. I see you have changed. Did I interpret correctly that here should be arrows?
Yeah.
Okay. Do you plan to, it's not mandatory, but you may decide to add one more panel. Like what would happen if one creates an interface?
By the way, are we being recorded right now?
Yes, yes.
So everything we talked about right now, it's going to be available on YouTube?
Yes.
Okay.
So if you like panel D, and again, it's your free choice, but just recommend it time allows. The occupied orbital on the idle and unoccupied orbital on the spherical interface. The element always wants to follow thermal distribution. Occupation from here will drop down there.
Okay.
Which means if you remove elements from here, it creates additional elements here, so the ground state of this interface will make a charge transfer. Careful.
All right.
So, everything here is to be a preview, whatever you want. Could be beneficial. First, maybe check the new version, but if you just copy paste figure and type here. just send it to Joe after the recording thesis. So you can do whatever you like, work on then make a screenshot, then cut it.
So I directly imported the PDF into my what Word document. You're saying I should
PDF or GPG or whatever.
So you're saying I should directly take a screenshot of my PDF and put it in there?
Right.
Okay.
It may have a little lower quality of the image, but it will be more reliable.
All right.
Also, here there are some features, and you may label why, what are the benefits. When we go later, next analysis orbitals, it would be you may check which of the orbitals occupied and unoccupied correspond to which peak. Okay, so it will make more create connection between figures and make the story consistent. And later, when you analyze initial excitation, photo excitation, if you have labels, you untie your hand and you can tell, okay, I'm doing excitation from feature C prime to feature D. And it will be more illustrative, explaining how excitation is happening.
All right. So what's the easiest way to add these?
I did send you a PowerPoint where showing. So I did copy paste the image here and then just add text.
Okay. So then after I add all this text, I just screenshot it and then paste it into my Word?
Mm-hmm.
Okay.
It is at least what I do when I write papers. Maybe you can find some better ways, but it's one of the options. Here, it is not mandatory. Again, it's very secondary, but if you maybe postpone it to after urgent things, after the presentation, or when you're absolutely sure that free time. Take the same system, replace back all iodines and sodium on the letter theory,
Okay.
and redo a train structure in this system. It is here. It is for different system, but this is the system without doping, and this is system with doping. So one can see that there these features at the Bandgap were not available and became available after you introduced doping.
Okay.
And this one, which is done with very late keyword, it shows what happens after promoting from homo to human.
Right.
Creates a little unoccupied, creates a little occupied. It's not a big sign, but it is very illustrative.
Okay.
Telling what I mean. So it's just an option. This is not right. Something is maybe you can share with your strength file.
Okay.
There shouldn't be transition at zero. It sounds not right. When you look into the Bandgap, balance current has all states up to the last one occupied, conduction, then has everything unoccupied. So the feature in absorption at zero gap would appear in such configuration.
Okay.
If there is a degenerate orbital, one is filled and the other is unfilled. For this, it will be zero transition energy. you have situations like that and that, you should start. So let's inspect the OS strings.
So I should send you my oscillator strength.
Or just send a link at which location on the cluster is.
Okay.
So,
If it helps, I used Yulin Han's method of creating my oscillator strength. So about a week ago, I had difficulty, and then you and Yulin Han took a look at it, and then you sent me directions as to how he did it. So I just copied what he did and created my OS string file.
okay. Let's check together. But I need to look on the file.
Okay.
So we are not going to recompute any data. We just need to analyze where is available. This figure shows that some of the results that we have limits of trustability. Okay, this is an important aspect. Committee members will ask you that. Even may hide this from thesis if you know try it. But committee members will request you to show. So
Wait, show what exactly?
show this figure and explain what it is.
Okay.
And this figure, in some sense, disfavors a lot of your results. You just should realize it and have a general plan for the correct time. But at least understanding what is here. So, can you explain what this figure shows?
Okay, so as I understand it, this is a fluctuation graph. It shows each line is a different orbital. So this is my conduction band. No, this is my conduction band. This is my valence bands. Okay, and then so each line is a different orbital. It shows how each orbital's energy fluctuated to a time. So if I remember right, if all these lines were straight, that means there would be, it's like a constant the temperature.
Yeah, like 0 Kelvin.
Okay.
Do you remember for which temperature this figure has been done?
I can't remember, but
let's check. So what is the blue line here?
I think that's my HOMO, right?
So it's because it is in the conduction band.
Okay.
And this one is price
Right.
And what is this?
That's the bandgap.
Yeah. How does it change with time?
It becomes smaller with time.
Okay. Now, is there a paradox between this figure and this figure? Here you claim that your gap is about 1 over kilo, and there you cannot say what is the gap. It changes from 1 to 0, right?
Well, for that density of states, I was looking at that at constant temperature, so I wasn't seeing how that density of states changed.
For DOS figure, you were taking temperature for 0,
Okay.
no temperature. But in real life, it's not possible to achieve 0 Kelvin. Right?
Okay.
So in real life, the energy support will start fluctuate and gap shrinks. Sometimes it shrinks even to 0. And you need just to realize it and see that it is one of the major mechanisms that may undermine trustability to the results.
Okay.
Possibly there are ways to mitigate it, but you need to realize it and see how strong this affects. So the temperature fluctuation changes the gap from 1 eV to 0 eV. Basically, it makes it form semiconductor for matter.
Okay.
What is the reason why temperature makes energy of orbitals change?
I mean, as the temperature increases, that the electron is going to absorb all that heat from the increase of temperature into vibrational energy. So it has more energy, and so that energy is going to make it easier for the electron to jump between orbitals.
You're telling the correct thing, but you're not answering questions. You're not answering this specific question. What your answer? You are kind of taking a page in your memory or in a book. Is a correct answer to the question: why electrons jump from one orbital to another? And here you do not have jumps yet. You have just energy. Energy gap between occupied and unoccupied. Why it changes? Just think. Do not remember. Do not try to recall. Just analyze.
Okay, I'm going to try a different answer. It's due to non-adiabatic dynamics. So non-adiabatic dynamics, the nucleus vibrates. When the nucleus vibrates, the corresponding orbitals position changes. All right. So then, as the time goes by, it's also natural that the band gap between the HOMO and LUMO is going to change also with non-adiabatic dynamics. So when you're taking into account this non-adiabatic dynamics, the nuclear vibrations, and you're also taking into account the temperature fluctuations. From my understanding, I'd say those two things are the main factors in reducing the band gap.
In this figure, there is no non-adiabatics.
All right.
No. The energy of each orbit does depend on positions of nucleus.
All right.
So it's like potential energy, right? If you change positions of atoms, total energy of system changes. But if you set up that positions of atoms depend on time, then it means that the energy which depends on positions of ions also depends on time.
Okay.
So you just need to explain this. Since atoms are not steady anymore, they oscillate. The change of positions of atoms change energy as one is moving along the complicated potential energy surface. The energy will change. And for probably this is not 300 Kelvin. It looks more like 1,000. 300 Kelvin, it wouldn't force the effect to zero. But the degree how much the gap is energy of each orbital, how much it's changing, is a little bit more than one may expect. Typically, one would expect that thermal energy is kT, or room temperature kT is like 0.03. However, here we have it like it changes by 1 hour. So just keep thinking of this paradox and be prepared. But the first thing you ask for sure. Okay? So the friends of critics, but doesn't like this numerical observation. Okay? Just try to make it comfortable. I just cut and paste it. So I keep your panels, cut and paste it on the PowerPoint, and then make that screenshot of this. Okay? Because looking them as individual figure will expire patience in the reader. And here you can take all that. Okay. Right now, probably most important thing is to work in the rest of the captions in the main body text. But please be prepared that later the thesis size of the font here is use really deep images. Okay? Compared with this one. Or images. Huge.
So is everything that I say in that caption correct?
It seemed correct to me.
All right.
I will read. I will read one more with some more time in communication. I don't see errors like that.
I have another question about this. Can you scroll up? Can you tell me what this gap is here for my 300K? Is it important?
Mm-hmm. It is. I would say it is interesting.
So
by the way, if you could do such image for each temperature and arrange it in the same format as you do here, it may bring more understanding. But when the change of energy of orbital versus time is flat, it means it is not immediate connection, but it is a signature that non-adiabatic coupling between these orbitals is expected to be squared. In this space range, the HOMO is not changing much in time, and HOMO is not changing much.
Alright.
So their transition between HOMO and HOMO is small. If you look on the orbitals that are higher in energy in this spot, they intersect each other and they have some feature of more rapid changes, and this corresponds to higher values of rate.
Right.
And if temperature increases, it will be much easier to analyze such images. When temperature increases, all orbitals, including HOMO and HOMO, start to perform significant oscillations, and which leads to non-adiabatic couplings in the gap region.
Right.
So when you look at the smaller temperature, so nothing, something, nothing, something, and if you look at this number of if you look at high temperature, it's basically constant.
By the way, for this, I know that these two are different from that. So in PMD, can you remind me what settings you use to make this?
Let's finish going over all figures and then we'll open the
Okay.
Okay, I do worry. Oh, okay. Here. So, you may compose it. What did you select? which orbitals to put? What was the principle?
I just selected these orbitals at random.
Oh, right now I'm not sure if there is time to fix it, but ideally I would select those orbitals which provide maximal transitions in Oscillator Strength.
Okay.
And maybe I will show both home and home, because home and home is always interesting. Panels and here it's just middle.
Okay, so what do you want me to say in the caption for waterfall graph? I mean, do you just want me to mark where the conduction and valence bands are, where the bandgap is?
Yes, and after you make these markings, you can change region of the sodium or iodine, sodium. Okay.
Yeah.
Yeah, for this one it will be a lot of work to explain. But here the quality is not so bad. You need the large font for these images. Here the font is too small. And here you probably won't need until you explain by your own words and then I try to.
Okay.
No, this just in case. And please reply to my other email. This one I'm using it for project pictures.
Okay.
I'm not checking.
Got it.
Okay, so you got this thing that you were analyzing the tech together, now let's go to this computer and quickly check. Oh. Let's see if we can do this. I think it will be. I'll try to. You can take a bit of
I have them on my laptop. I can show them to you.
No, it's. They were much close. The quickest thing would be just to download the. So if you instruct me which therapy they are looking for, they can do. So where should we go?
Alright, go to my directory, the Chem 676 / Kevin Lima. Alright, go to PBTE. Interface 100.
Orbitals? Or for charge?
Check orbitals first.
Okay, and what's the number of lumen?
Okay, so HOMO 718, LUMO 719.
But
wait.
Here starts with 13. So,
Yeah, I'm not sure why they start with 1300. I don't know. Am I using the different files?
yes.
Try this directory. Global project years, and then instead of interface 100, try interface. No, not interface 111. Interface 100. So instead of this
Okay.
111, interface 100. Okay, so it's almost 718.
Mm-hmm.
Oh shoot, I can't remember if it's TFT or SOC.
It will be different 2 times.
All right.
The DFT will be 7 something, the SOC will be 14,000, 1400 something.
Okay, so yeah, I'm using the 700 one.
Okay. So we will just you remember how many sodium iodines
2 sodiums and 2 iodines.
and how many reds and how many tolerates?
Okay, together they're about 300, but if I remember correctly.
No, let's look exact. So 142 each. So first I'm selecting this Oscar type of frame. And the image is quite pathetic, so I need to do some moves to make it more better. Presentations, dynamic ones.
So you have dynamic bonds for drawing method?
It is not for orbitals. The image is composed of the model and isosurfaces on the top of it. So I need to do dynamic bonds and also the those that make the image, the size of the sphere is much smaller. And for images it is probably better to have the background display the ground instead of the no on the top.
How do you get to that color thing again?
Brackets, colors, display the ground inside.
Alright.
And now we need to make another object to Numerator, browse, select this purchase fee, and so that at the bottom of the list it will show cost for church density.
So you right-clicked on Pascal and you clicked Add New Representation, or you just added another molecule altogether?
Edit another mode. You see, there is a list postcard and then per charge.
Okay.
So after I avoid per charge, it doesn't show anything. It looks like a little scary that the model is not here.
Okay.
But if one takes representations, it shows like here points when not visible at the solid surface. And then rather than move this
So you select that first and you went to graphics representations. All right.
And for better visualization, so it's basically here you select convention of maybe color or unoccupied orbitals with specific color like pink, transparent, it's just a little decoration. And then we can make a screenshot.
So select bar chart, graphics, representations. Then I select this draw solid surface, and that material is solid. And then I can change this color to whatever, pink, green, red. All right.
And here to go back to this postcard, and there I did create dynamic bonds and one there was. So here, if I put this large diameter, then it looks like form. If it's small one, it looks like form.
All right.
Probably there are some advanced ways, but I just do description. Choose sufficient. Okay.
All right.
I'm just create this. Show that it's infinite. Good?
Yep.
Okay. Right. Stop screenshot. This station.
So even like what you just showed me is on YouTube too?
It will be.
Okay.
All
right. Anything else you have to tell me? All right.
Just do the best you can and send me maybe by 2 p.m., 3 p.m. so I can print and show the things. By 5 p.m. we will be done, so if we will not be there, I'll just have to pass with you. In the meeting we will go on, but it will be different subject, presentation, research, and discussion.
All right. So should I be there for the part from 5 to 6?
You're welcome to join. It will be fun science, but it is not mandatory, and it will be. I do not see direct connection to your research. So really just go in your views, some fun science, same as visiting seminar, but not of immediate benefit.
Got it. All right. So as always, I have a lab from 3:30 to 5:30. So I may or may not make it by like in that 4 or 5 like interval.
Okay, that's fine. That's fine. I think we are on a good track. Plan.
All right. So I should come in tomorrow at like 5:15 to collect all the feedback.
Would be great. Would be great.
All right, so I can come here, collect it, and then head out if I want to.
Yes.
Okay. All right, got it. So yeah, I'll send all my like revised figures plus a very rough draft of my results section to you tomorrow by 1 or 2.
Okay. Very good.
All right, see you tomorrow.
See you again.